Greetings, physicists. This video will be talking about how waves interact with other waves. It's a very interesting subject, and we'll just talk about, well, first we're going to talk about how waves react to boundaries. So let's draw a string on which I have caused a wave to happen, and it's going to travel in this direction. And let's suppose that I don't tie the other end of the string. So this end of the string here is free to move. As this wave travels down the string, it will get to the end and it will come up to here, and then it will travel right back. It'll kind of bounce off of that end, even though it's almost like there's nothing to bounce off of. But we'll say that this point right here, the air, is a different medium. So the wave moves all the way down the string to that different medium, to the changing medium, and essentially it reflects off of it. So anytime waves try to change medium, there's a little bit of reflection, there's a little bit of transmittance happening. And in this case, the wave reflects back, and so what will happen is it's going to change direction and try to go right back, and we will get this situation where the wave is traveling right back. Now, I didn't draw it very well, but if the wave had this shape and this amplitude and everything, it will have the same shape and the same amplitude on the way back, just moving the opposite direction. So that's with what we call a free end. So this end of the string was free to move. Now let's do a different situation. Let's take that string and attach it to a wall and send a wave towards it. When it gets to the wall, it will reflect, right? The wall again is another medium. It's not the string stops. So the string medium ends and the wall begins. So we have a barrier between two media. But when it reflects off the wall, it reflects on the opposite side. If it had a positive amplitude here, it will have a negative amplitude here when it comes back. And otherwise it will have the exact same shape and everything else that it came with. It just sort of goes from pointing up to pointing down. And that's the pattern we see with reflecting waves at barriers. Okay. Now what you can do with this little experiment, you can send two waves down a string, make two little pulses, and they travel. And let's assume these waves are identical. And then the one in front, when he hits, let's say this is a free end string. So we're going to get down to this end, and after the reflection, this first wave will reflect first and start going backwards, but the second wave will still be going forwards. Can you picture that? And then they're going to overlap with each other. There's going to be some point in time where they both try to occupy the same space. And what you see when this happens, this is much easier to draw if you had if I could make this an animation, but still images, I can sort of show it. So when they come together, they get, briefly for a moment, they look like one big wave. So we have this wave going forward, this wave going backward, and then right at some time, right at the point where they overlap, that's this point here, their amplitudes, let's say this wave had amplitude A, and let's say they were identical waves, so this wave also had amplitude A, they will overlap with, my Michigan accent coming through, they will overlap with amplitude 2A, briefly. And then they will pass through each other. So what you're picturing is both waves are in there, and one is going this way and one is going this way. They just happen to be stacked on top of each other. And then as they pass through each other, now, and I have to label these waves, right? Otherwise this is really hard to visualize. This is like wave 1 and wave 2. This is wave 1 and wave 2. This is wave 1 and 2 together. And then afterwards, wave 1 keeps going forward because it hadn't reflected yet, and wave 2 is now going backward, and they still both have amplitude A. my bad drawings notwithstanding. So, and they don't change their speed, they don't change anything else. It doesn't seem as if it really matters much to anybody other than the amplitude happens to increase for them while they're there, and it's additive. Now, so that's situation one. We call this, because when they overlapped, they made something bigger, they added their amplitudes. We call this a constructive interference. They interfered with each other. And that interference led to a bigger amplitude. So let's try doing it the other way. And I'm going to do basically the same experiment, but I'm going to fix the end of the string. Okay? And so I have the string, and we'll say the same exact thing, waves 1 and 2 sent to the right. And they're going to get to the edge here. Wave 1 will bounce first, while wave 2 is still coming forward. Oh, I even drew that wrong. Because when wave 1 bounces, because the end was fixed, it's going to bounce and reflect on the other side. And we're assuming they both have amplitude A. And so this is now wave 1, but he's on the bottom side coming backwards after he bounces. And wave 2 still hasn't made it, right? And so they're going to overlap at some point. Well, when they overlap, because now they have amplitude A and amplitude negative A, right? So when they overlap, this is what we get. We get this point, and they perfectly cancel each other out. This is assuming they had the exact same shape and everything. So you get 0 amplitude at that point. Now both waves are there. 1 is still going forward, 2 is still going backwards. It's just that their amplitudes have overlapped in such a way as to make them completely flat, completely 0 amplitude. And when they finish, this is what we see. We see wave 1 continues on, or sorry, this is wave 2, I'm sorry. Wave 2 was on top, and then wave 1 down here still going this way. So they just kind of pass each other, again, not changing their speed or anything else. The interference doesn't affect anything but their amplitude at that moment, and they continue with the same amplitude they started with. So because this happens and they sort of destroy each other, they get rid of their amplitudes, we call this a destructive interference. And so this is like for individual waves, which individual wave pulses happen. You might see this on a test. Sometimes you'll get clever test questions like this. You have a wave 1, and wave 1 has this shape. And he's moving that direction. And then you have wave 2, has this shape, and is moving this direction. What happens, what is the amplitude of the wave when they overlap? And those are fun. You have to do some creative geometry with them, like if I were to superimpose them over each other, I'm subtracting their amplitude. So what does that look like? Well, that looks like a big square, but the triangle is like this. It's going down. And so anything that's shaded is where they overlap. That gets taken away. What's left? So the amplitude of the wave that overlaps is going to look something like this at the point where they overlap, this point here. So, and that happens with waves that these may have the same kind of amplitude A like this, but they don't have the same shape. Or if you had, we could do another example where there's like a wave that has amplitude, 2A, overlapping with a wave that has amplitude 1A. And so the leftover wave right at the point of intersection is 1A on top. That's what's left over. Okay, so those are constructive and destructive interference type problems. Now, what's really interesting is when you make a bunch of them. So let's say I have a wave pulse generator that just keeps making waves on a string. over and over and over, a constant series of them. And they travel to, the right. And then we let this end be free. Those waves are also going to reflect back. And so and I'll try to, so imagine at any point, this is going to be hard to draw. And then there's the reflected back waves. And then so like this, and like this, and like this, and just pretend that was possible. And then they're going to come towards each other, and there's going to be a certain pattern of overlapping. But if this is a continuous process, and i.e. whatever's shaking the end of the string to make the waves doesn't ever stop, what we will get is an overlapping pattern on the string. And it really depends on how they line up. So let's draw some examples. Let's say that the forward waves go like this, and then when they reflect back like this, such that the peaks and troughs exactly line up. Well, every time a peak lines up with a peak, you get a constructive interference. Every time a trough lines up with a trough, you get a constructive interference. So that kind of wave pattern will make a bigger amplitude. It won't change the frequency of the waves, but it will make that, if this was the amplitude here, it will make it twice as big, right? And this will be an effect that increases the amplitude of the wave. It's constructive. It's just happening for all waves at once. And what we will get is a standing wave, right? If you've ever seen someone jump roping, and they swing the jump rope like this, and then they swing it back, right? What they've done is they've actually made a wave travel on the string that's essentially half the size of the string, but they've picked the right frequency so that the return waves just line up with each other and make themselves bigger. That's jump roping. But you can also go the opposite direction with it, right? What if all the waves going forward went this way, but when they came back, they lined up this way? And this happens. Well, we've got a peak with a trough, a peak with a trough, a peak with a trough. That's destructive everywhere. Then you get a flat line. There are waves traveling on this line, but their amplitudes are completely canceling each other out. That's a destructive interference, and that can happen. So, for instance, if you build concert halls, this is a big deal, where you go inside and there's all the seats. Here's like the top-down view of the seats, and the stage is up here, and you've got these big speakers on the stage. And each speaker is putting out its sound wave. Now, I'm going to draw the sound wave like a transverse wave, even though I know it's not. And you play the sound wave here, and you play this sound wave here. And if you have a spot where a peak and a trough overlap, then the person sitting in that seat is not going to hear a very loud sound. It's going to feel very dim. But if you have a spot where a trough and a trough overlap, the person sitting in that seat hears a really big sound. So this is acoustics, right? And so if you look at the surface ceiling of these concert halls, there's all these like tiles, and they're angled at different angles. Well, they're trying to reflect sound in such a way that everyone can hear it. They don't want this kind of thing where the sound cancels out. They call that a node. And if you have a node in your room, then no one wants to sit in that seat. So you got to be very careful designing concert halls and things. So, this concept that whenever a peak and a peak and a trough line up, this is called a resonance. Effect. And it's very big in the world of physics. We use it all the time. Your microwave oven, for instance, operates on a resonance effect. You may have learned in chemistry that molecules vibrate. So I'm going to draw a molecule for you. Okay, that's a water molecule. And there are two chemical bonds there. Each of them is between this oxygen and a neighboring hydrogen. And what happens is this bond here is not a spring, but we're going to model it like a spring. Pretend it's a spring. Pretend it's just this spring, and we already learned that you can oscillate on a spring, so pretend that this hydrogen atom is vibrating back and forth. And because of what we know about oscillations, it does so at a fixed frequency that is independent of its amplitude. So it has some frequency that it vibrates back and forth with. All right? Now let's imagine a light wave. Light waves have peaks, troughs, and it's traveling at a certain speed. And because it has a certain speed, these things these peaks will pass by with a certain frequency, a certain regularity. So now imagine that we shine a light wave at this hydrogen bond. If we pick the right frequency, then every time, so if we were to graph the function of this chemical, right? The hydrogen starts out at max amplitude. It's a cosine function of the position is, right? This is position of that hydrogen atom versus time away from that oxygen atom. It's a cosine function. At some points it's really far from the atom, at some points it's at the equilibrium position, at some points it's really close to the atom, right? It just keeps going back and forth. So what we're going to do is we're going to take this light wave, and if we pick the right one, if we pick the light wave with the right frequency, then all the peaks of the light wave will hit that hydrogen atom when it's at max amplitude, and all the troughs will hit it when it's at other max amplitude like this, and it will be a perfect superposition. And because that all overlaps, that will increase the amplitude of its oscillation, which will give it some energy. It'll have a bigger oscillation, and that energy expresses itself as heat. So what we have in your microwave, plate of food on the inside, here's the box around it, and up inside the edge of the microwave there's not really a light bulb, there's like a magnet essentially that creates light, but we'll pretend. So pretend we have the right light bulb. This light bulb is the perfect frequency to put out the kind of light that has the same oscillatory frequency as a water molecule. And so when you shine it on food, here's some amount of food, whatever food you're eating, almost all the food we eat has water in it. That's a big component of stuff that we eat. So you're shining light, and the light's just hitting those hydrogen atoms at their resonant frequency, or those water molecules at the resonant frequency, and making them heat up. So you're shining light on your food. Now they call it a microwave because if you're looking at the electromagnetic spectrum, right, you have the big waves and the short waves and the little tiny waves. There's a little section in there, waves that are between 1 meter and like 1 centimeter long, called the microwave frequency. They're too big for us to see, like your eye can't see microwaves. So if you were shining this light just at your body, you wouldn't notice it with your eyes. You would feel your insides heat up because you're full of water. But that's how we do it. We cook using shining light on stuff. And it works because of this concept of resonance. Okay, so that's it. That's resonance, that's superposition, that's reflection.